Hi everyone, so we're going to do a couple of introductory examples on moments, and hopefully you've had a chance to have a little read of the introductory notes. So you will have seen that the moment of a force is the magnitude of the force times the distance, and the distance must be the perpendicular distance to the line of action of the force. Okay, so that's really important that you get that straight in your head straight away. Okay. And we're going to go through a couple of examples. And basically, the moment of a force is a measure of its capability to turn its rotational motion clockwise or anti-clockwise. Okay. And quite often when you're doing this, sometimes people get a little bit confused if sometimes it's really obvious, sometimes it isn't, about which way a force would make something move. So in this one, we're going to have a look at the sum of the moments of these forces, 3, 4, and 5, about this point A. Okay. So if ever you aren't sure and you just want to do a check, you can always just put your pen on the point and then just kind of tug the paper in the direction that the force is going. So this one's saying the force is going up 4 newtons. So if we think about that, that's going to cause us to move anti-clockwise if this point is fixed and rotating. And this one at B, the 5 newtons downwards this time, if we imagine that force pushing downwards, that's going to cause a clockwise motion. Okay, and it's really important that the anti-clockwise and clockwise are differentiated between each other, and that we tell the examiner what we're going to do in here in this question and which direction things are going in. Okay, so what I'm going to do, I'm going to take moments about point A. Okay, because that's what I'm asked about here. So this is the point that we're thinking about turning between. And one other point that I forgot to mention before is if you've got a force that's acting directly at a point, then that's not going to have any turning motion at all. The moment's going to be 0. So that 3N is pulling directly down. So it's not going to turn the paper around A. Okay, so there's no moment there. And really the reason as well, this would give 0 because the distance from A is definitely 0. So whatever the force is times 0 is going to give us no moment. So it's got no turning capability there. Okay, let's have a look at taking moments about A. And I'm going to tell the examiner that I'm going to take clockwise. So let's go that way. I'm going to take clockwise as positive here. And we've seen that before, haven't we, telling them which direction we're going to take as positive in other questions. Okay, so again, just to make that point, the moment of the 3 Newton force about A is 0. So that force there can be discounted from our calculations, or we could put 0 in if we wanted to. Okay, so let's have a look. We want the sum of the moments, and this is basically going to give us the resultant moments. Which direction, if all of these forces were acting at the same time, is this thing likely to turn about A if that was where our point was fixed? Okay, so the moment's the magnitude of the force times the perpendicular distance. So that means if I think about clockwise first of all, this 5 newtons was the one that was going to turn us clockwise. So 5 times my perpendicular distance from my point, which is this distance, which is 6. And then for this one now, the 4 newtons is turning us anti-clockwise. Okay, so I'm going to put plus there for now, but this is now going to be in the negative direction because I'm taking positive as clockwise. So actually here, this is now going to be in the negative direction, and it's going to be this 4 times this perpendicular distance. So that's going to give me 30 minus 16, which is 14 newtons meters. So that's our units for moments, 14 Newton meters, and that's going to be clockwise because it's positive. Okay, and if I got a negative answer here, then I'd get, if it was minus 14, I'd get 14 Newton meters anti-clockwise. So that's what's happening here. That's the overall effect that's going to happen for this question. Okay, so that's our first one done. Our second one then is going to be another question, but this time where the forces aren't necessarily perpendicular, so it's not quite as straightforward. So let's have a look at this one. So here's this example. So the following diagram shows forces acting on a laminar. Now a laminar, you might have seen this definition from the M1 book, the first mechanics book, but on a laminar, it's just basically a surface that's got area but no thickness. So I suppose a bit like a sheet of paper, but it's infinitely thin, and we don't need to worry about the weight of a laminar either. Okay, so calculate some of the moments of these forces about point O, and here's our point O down here. So my 3 Newton force, although it's not acting you know, it's not drawn here, I can, because it's a vector, just kind of go, right, well, that's the direction of my motion. So this 2 meters here is absolutely fine. That's our perpendicular distance. So that distance is sorted for us. So that one's okay. For this 7 newtons, then I need a perpendicular distance, and I haven't got that yet. So what I'm going to have to do here is I'm going to have to work out this distance. I'll call it x. So that's now going to be my perpendicular distance for the action of this force about O. And again, you know, when we think about clockwise and anti-clockwise in a second, if I think about this 3 newtons, it's trying to pull the paper that way. So again, that's going to be clockwise, and the 7 newtons is trying to pull the paper that way. So that's going to be clockwise. So these are both going to give us clockwise motion when we're looking at our answer. Okay. So let's tell the examiner what we're going to do. We're going to take moments about point point O in this question. And again, I'm going to tell the examiner I'm going to take clockwise as positive. Okay, so that's what I'm going to do. So let's have a look at this. So this one, first of all, here, we're going to have a look at this 3 newtons, where our distance is 2 meters. So for that one, again, our moment is going to be equal to, that's going clockwise, so that's going to be positive 3 times this perpendicular distance, 2. And then for this one, again, this was pulling us clockwise as well, so it's going to be plus positive 7. And then I need this distance, and that's then just going to be a bit of trigonometry, because we've got a right angled triangle here. So if I look at this, I've got the hypotenuse and the opposite. So sine of 30 would be opposite over hypotenuse. So x is going to be 6 times my sine 30. Okay, so x here is going to be 6 sine 30. Okay, sine 30 is a half. If you don't know, you can just do it on your calculator, but that's definitely a half there. So that's going to be 6 times a half, which is 3 there. So this is going to give me 6 plus 21, 27 Newton meters. And again, it's positive, so that's telling me that it's going to be a clockwise motion. Okay. Final question, just in these initial examples, is one with vectors involved. So here's our question. The force 6, 3, if it was in a column vector, so 6i plus 3j, so 6 horizontally and 3 vertically, newtons, is applies to a point A of a lamina, where A has got the position vector 1, 4 meters relative to the origin. Calculate the moment of the force, and we're asked to do 2 separate things here. Once about the origin, and then about this other point that they're telling us is the point 2 minus 1. So I've just drawn some axes here to get us started, and obviously the origin is going to be there, so that's going to be for this first bit, the point that we're turning around. It says this force acts at point A, so point A has got position vector 1, 4, so let's just put point A on here. So there's that position vector, that point A. And it tells us this. Now we could obviously draw this as 6 across and 3 up and get that vector drawn like that. But because I want my motion to be perpendicular to this point, it's going to be much easier if I split that up into these 2 different components and have 6 newtons across and 3 newtons up. And that would be exactly the same as this resultant vector that would happen if I did 6 across and then 3 up. You know, we would get that overall force there. So it is having the same effect here. So that's absolutely fine to do that with vectors. And it's quite nice with vectors that you can split it up into those perpendicular components to begin with. Okay, so let's have a look at part A. And again, I'm going to tell the examiner, this time I'm taking moments about the origin. And I'm going to take clockwise as positive. Okay, so let's have a look at this. So again, that 3 newtons pulling upwards is tending to turn me anti-clockwise. So for that first one, that's going to be anti-clockwise. So that's going to be minus 3, negative because it's anti-clockwise, and I'm taking clockwise as positive. And then the 6 newtons, if I think about the way this is pulling, sorry, 0.8, this is pulling, it's pulling me that way. So again, that's going to be clockwise, so that's going to be positive. And the distance here is going to be, let me just see, so that was 1, this distance is going to be 4. So that's minus 3 plus 24, 21 newton meters. It's positive, so that means it's in the clockwise direction. Okay, and don't forget this negative is because this one's pulling anti-clockwise, this positive because this one's turning clockwise. So that's that bit done. Last bit then, part B, we need this point B, which is 2 minus 1. So here's my point B down here. So this is where I'm turning about now. And again, I need to think about, I'm going to take moments about B this time. So moments about point B. And if I think about now, if I'm there, this 3 newtons is going to be pulling me that way. So about point B, it's tending to turn clockwise. And my 6 newtons is pulling this way. And again, about point B is going clockwise. So both of these are going to tend to turn clockwise about point B. Okay, so again, taking positive in the clockwise direction. Let's have a look at what's happening. So my 3 newtons is a perpendicular distance of 1 metre away from B. And my 6 newtons, both positive because they're both pulling clockwise, my 6 newtons is a perpendicular distance of 5 from B. So that's going to give me 3 plus 30, 33 newton meters. Oops. And again, clockwise because it's positive. Okay, so that's 3 sort of basic examples of that, and I'd like you to just for today have a bit of a practice of those. So the first couple of exercises from the textbook, just as a bit of practice of that, and then we'll move on to equilibrium tomorrow. On Wednesday. Thanks.